Hey guys, I wanted to show you one more kind of problem that kind of piggybacks on the problem we did in class today. Here, instead of asking about the potential energy of one particular charge, this asks about the potential energy stored in the system. What does that mean? So the idea is that this system has a certain amount of potential energy. I don't know, let's just give it a number. Say it was 10 joules. If I said that the system has 10 joules, well, these are all positive charges, and positive charges like to repel each other, and you can imagine that that creates the potential for movement. And so what's the maximum amount of movement I could create? Well, if all of this potential energy gets converted to kinetic energy, then I would have 10 joules worth of kinetic energy, and these guys would all be flying around at different speeds, and I could figure out how much speed each one had. How does the energy get distributed? Well, that depends not only on conservation of energy, but also on conservation of momentum. That's the end game. Before we can get there, though, what we first want to do is how do we get that number in the first place? How do we figure out the potential energy of the system instead of just making up a number and saying it's 10 joules? Let's calculate it. Okay, so the trick to a problem like this is to say that the potential energy stored in the system is the potential energy I have to add to the system in order to build the system, in order to add each charge. What do I mean by that? Well, let's pretend you start with an empty universe. You start with an empty universe. There's nothing in it, right? And I want to build something that looks like this. So the first thing I'm going to do is I'm going to move this charge into my empty universe. That charge has 2 coulombs worth of charge. It starts at infinity, and I move it into my empty universe to the spot that it's supposed to be. Now, how much work do I have to do on this charge in order to move it from infinity to there? 0. Why 0? There's an empty universe. There's no forces in this universe for me to overcome, and so I get to put that charge in for free. Okay? So the idea is we're going to move the charges in one at a time, and we'll figure out the work to move each charge in, and then at the end of the day, we'll figure out the total work by summing up the work to move in all the different charges. Okay, so at any rate, the first charge is free. It costs me 0. Okay, so here I now have my first charge. It's in my universe. Now I'm going to take the second charge and I'm going to move it in. Where does this second charge start? It starts at infinity. So here's my 3 coulomb charge. It starts at infinity. How much work do I have to do on this charge? How much do I have to push it in order to put it over here? In this case, definitely not 0. Why not 0? This charge creates an electric field. These are both positive charges. I have to fight against this electric field the entire time in order to move that charge there. That means I need to invest some energy in moving this charge, and that invested energy becomes potential energy in the system. So one way to think of this is to figure out the work I have to do, and the work is something like force times distance. It's a little fancier than that, but that's the main idea. The issue with doing it this way is that the force on this charge keeps changing when it's at different locations. So the force here, I'm just making up a number, it might be 3 newtons, and the force here is 2 newtons. How do I do that? Which number do I use? It's kind of a pain in the butt. If we had a calculus-based class, we'd use an integral and it wouldn't be a big deal, but we don't have integrals in this class. Instead, the way we're going to attack this problem is not by thinking about forces, but by thinking about potentials. We say that we change the potential energy of a charge by an amount Q delta V. Okay, so what does that mean? That means that this guy, in addition to making an electric field, also makes an electric potential. That potential is felt everywhere in the universe. The 3 coulomb charge feels its potential at infinity when it's out here, and it feels its potential a distance 1 meter away at its final location. So what is the voltage? What is the potential that a 2 coulomb charge makes? Well, the potential, V of R, is KQ over R. So if I want to figure out the change in potential energy of this charge, I can say that it is delta V. So what's delta V? That's V final minus V initial. Remember, this is the voltage created by the 2 coulomb charge. So if I were to write this, I would say K times Q, it's the 2 coulomb charge that makes the charge, times 2, divided by, well, its final position is right here, 1 meter away, 1. that is the final voltage. What's the initial voltage? Well, it's the voltage up here, so that's K times 2 coulombs, because again, it's still this charge making it, but now divided by infinity, because it's infinitely far away. So that's 0. Anything divided by infinity is 0. If anyone tells you otherwise, they're crazy. Okay, so that's the change in voltage. What's the change in potential energy for this particular charge? The change in potential energy is the charge that I'm moving times the potential difference that I move it through. The charge I'm moving is this guy, the 3 coulomb charge. So this is 3 times delta V, or 3 times 2K, or 6K. And this guy K, of course, is 9 times 10 to the 9. It's just some constant that we drag along in order to make all the experiments match our theories. Basically, it's to make the units work out correctly. I'm just going to leave it as K because I don't feel like writing that over and over and over again. Okay, so this is the extra potential energy I add to the system when I bring in the second charge. So let's get that cleaned up. Okay. So this is it cleaned up. The first charge was free. The second charge cost me 6K to move in. Now what I do is I'm going to move the third charge in. I'm going to take that third charge. I'm going to park it at infinity. And now it's going to land, when I finally end up putting it somewhere, it'll land here at a distance 2 meters away from the 3 coulomb charge. Okay. Just like the last one, this is definitely going to take some effort on my part in order to get the charge in there, because I've got to fight the electric field from 2 charges that want to push it away. But again, instead of figuring out the electric field, I'm going to do everything in terms of change in voltage. And so I'll say once again that the change in potential energy for this final charge is its charge times the change in potential. Okay, I know where this thing lands. This thing lands right here. So my V final is the voltage that this charge creates. So that's K times 2, which is its charge. And now, how far away is it? Well, it's 1 plus 2. It's 3 units away. So there's the voltage from this guy, but there's also the voltage from this guy. This guy also makes a voltage there, and that charge also is going to feel that. So that's K times 3 divided by, this is a distance 2 away. That's the final voltage. What's the initial voltage? Well, this is the same as before. The initial voltage is going to be 0 because it's infinitely far away. And you can think again, if you replace these two numbers, instead of being 3 units and 2 units away, if they were both infinities, you'd be dividing by infinity and you'd get 0. So in this case, how much potential energy does this charge gain by being moved from infinity to that point? Well, its charge, the charge I'm moving, is 2. So I take that 2 coulombs worth of charge and I say 2 times 2K over 3 plus 3K over 2. Okay, let me clean this up. Okay, so here I have condensed it all. It takes an additional 4.33K worth of energy in order to shove that charge in. Now, if I want to know what's the potential energy stored in the whole system, well, I just add it up. This is how much energy I had to invest in order to build it, so that's the energy that's available. The total potential energy of the system, I'll just call it potential energy, is W1 plus W2 plus W3, and this is 0 plus 6 plus 4.33. There's K's on all these. And so I get 10.33K. Okay, a couple of things to talk about really quickly. The more detail-oriented of you may get upset with me for writing this, because we said over and over again in class that potential energy is minus the work. And what am I doing? I'm just calculating work, and then I'm saying that it's equal. What happened to my minus sign? Well, I've been a little sneaky here, because the change in potential energy is equal to negative the work, but that's negative the work done by the electric fields of these charges. Those charges create electric fields and create forces that point away from them, and when I take my charge, I have to move it against, in the opposite direction of those fields. So these charges do negative work. The work done by charges, by the charges, is less than 0. It is negative, in which case this would apply. What I've sneakily done is I've said, I don't want the work done by the charges. I want the work that I had to do in order to overcome the forces by the charges. That's the energy that I'm putting into the system. So in that case, my force points in this direction, and I'm moving along the direction that the charge is moving. And so the work that I do to build the system is positive, and that is energy that I'm adding to the system. And so when I say these are the works, this is the work done by me rather than the work done by the charges. It's a subtle point, but if you were scratching your head and getting upset and thinking about writing me an angry letter, that's the resolution of it.